Hello and welcome you all to the lecture number 21 of this NPTEL course on electroweak interactions in the standard model of particle physics. And in this lecture today, we are going to introduce a very interesting concept, and that is the concept of gauge theory. And that is what we are going to do first for a U1 gauge theory, and this is what is going to give us quantum electrodynamics at the end of the day. And it's a fascinating story, and this lecture is going to introduce you to that. Let's get started. Okay, first of all, let's remind ourselves that what exactly we have done and what we are trying to do here. Now, individually, we have essentially set up the Dirac equation and the Dirac Lagrangian, which actually upon quantization talks about electrons moving freely in nature, right. So, that is what it does. On the other hand, we also had introduced the Lagrangian for the electromagnetic radiation. Upon quantization, what you can call that, that is essentially the describing the case of photons. Now, the question is essentially that how we can bridge these two things together, or how can we make the electrons talk to the photon. Now, you all recall that from the very beginning of our quantum mechanical exercise or this atomic and molecular physics, we know that whenever an excited electron comes down to a lower state, it essentially emits a radiation or a photon. Now, we never ask this question that how the electron actually can emit a radiation. This is simply because the electron can interact with a photon having its electromagnetic charge, and this is all indicating to what you call the quantum electrodynamics, or basically the interaction of the electron with the photon. Now, that is the main goal of today's task, is to actually have this interaction brought up by a nice symmetry argument, which we have already developed in part. Okay, so let's get started without much more words. So, basically we are trying to connect electromagnetism described in last lecture or last to last lecture, whatever, to the theory of electrons, which is described by Dirac equation. Now, what was your electromagnetic Lagrangian? So, this was essentially minus 1 by 4 f mu nu f mu nu. I am for the time being restricting myself to the massless photon, and that does not have the mass term that we actually talked about. And f mu nu is what you call the field strength tensor, where f mu nu actually has del mu a nu minus del nu a mu, right, where a mu and nu upon quantization is essentially what we call the photon. Now, next is what is the Dirac Lagrangian. So, the Dirac Lagrangian, if you remember, the free Dirac Lagrangian was essentially described by the spinors, the Dirac spinors psi bar I gamma mu del mu psi minus m psi bar psi. So, the first is the kinetic term and the second is the mass term. Gamma mu are the Dirac matrices, psi is 4 component Dirac spinors, psi bar is the conjugate Dirac spinors defined by psi dagger gamma 0. And when you do this Euler-Lagrange's equation, this gives you Dirac equation, which is like I gamma mu del mu minus m psi is equal to 0. Now, we have already explored that when we take a transformation like psi going to psi prime, which is e to the power I alpha psi, say something like that, where alpha is a parameter which is a constant, and this is what we call a U1 global transformation. Now, why this is called U1 transformation? Because you remember that when we discussed these possibilities of the group theory, like U1 describing a unitary group, and this is basically one parameter by which you can define this kind of a rotation, and that is essentially e to the power I alpha. So, that represents the transformation under global U1 transformation. So, psi going to psi prime is e to the power I alpha psi. If you define that, then basically you can see that your psi bar prime is psi prime dagger gamma 0, which is nothing but e to the power minus I alpha psi bar. So, therefore, you can have psi bar prime is equal to essentially psi bar psi, because it's simply the e to the power exponential parts gets cancelled, and on the other hand what happens to the derivative part, because when you take the derivative like psi bar I gamma mu del mu psi prime, the derivative does not act on e to the power I alpha, it only acts on the psi. So, therefore, you have e to the power I alpha I gamma mu del mu psi kind of a term, and that has to be multiplied with psi bar e to the power minus I alpha. So, this exponentially part gets cancelled, and essentially you have psi bar I gamma mu del mu psi. So, therefore, this term also remains the invariant. So, the as a whole, the whole Dirac Lagrangian that actually remains invariant under this global U1 transformation, and this is basically tacitly there in the Dirac Lagrangian itself, and that precisely gives rise to this Noether current, right, which is the conserved current. You have a relation like del mu j mu is equal to 0, where j mu can be defined as psi bar gamma mu psi, right. So, that is what we have already exploited. Now, let us do one exercise when we say that this U1 transformation is no more global, but rather we actually want to have a local transformation, or what you call a gauge transformation. So, this is the term gauge comes from. So, gauge in a sense it defines your length scale. So, you are saying that the transformation, the U1 transformation that we are defining, it has a spatial dependence. The parameter which defines the U1 transformation e to the power I alpha, that has a spatial dependence. So, then we define psi going to psi prime e to the power I alpha x psi, and similarly psi bar goes to psi bar prime, which is e to the power minus I alpha psi bar. Okay. So, alpha is alpha x, which depends on the space time, and this is a local or U1 gauge transformation. Okay. Alright, so we have defined a local transformation or gauge transformation, gauge U1 transformation. Then the question that we would like to ask is that what happens to the derivative del mu psi prime. Now, you remember that now because alpha actually is not a constant, but rather it is dependent on the space time. So, the del mu will act both on psi as well as on this alpha, and this is going to give us two terms. The first term when e to the power I alpha comes out, and you have e to the power I alpha x del mu psi, and the second term when the del mu actually is acting on this alpha x. So, that is going to give you I del mu alpha x into psi x into e to the power I alpha. So, therefore, there are two terms that you can see. So, therefore, the kinetic term which is psi bar prime I gamma mu del mu psi prime, what happens to that? That becomes e to the power minus I alpha x, right. So, minus I alpha x psi bar. So, this is essentially your psi bar prime, right. The first term is I e to the power I alpha x gamma mu del mu psi minus because इसमें एक I second term may already have from the derivative, and when you multiply another I, this becomes minus of e to the power I alpha x, which is this term, into gamma mu जो gamma mu है into del mu alpha x into psi x, right. Now, what you can see that this e to the power minus I alpha x and e to the power I alpha x from both these terms will get cancelled with e to the power minus I alpha x that is sitting here. So, the first term is going to give you what? This is going to give you psi bar I gamma mu del mu psi, right. So, the first term, the first multiplication with this and this is going to give you psi bar I gamma mu del mu psi. So, this is the original kinetic term that you have in the Lagrangian, but there is a second term now. What is the second term? Second term is psi bar gamma mu. Let me use the color exactly the way that I have done here. So, this is psi bar gamma mu del mu alpha x into psi. So, you see that just because that you have taken the alpha to have a spatial dependence, then there is an additional term in the kinetic when you try to actually find out in the transformed after the transformation on the psi that you have imposed, there is an additional term which is actually coming here, which is like psi bar gamma mu del mu alpha x psi x. So, this additional term essentially tells you that your Dirac Lagrangian is no more invariant under this local gauge, local transformation or the gauge U1 transformation, which is psi going to psi prime equal to e to the power I alpha x psi, right. So, this statement I think is clear to you. So, the Dirac Lagrangian is not invariant because from the kinetic term there is one derivative of del mu alpha which is creeping up, which makes or spoils the invariance of the Dirac Lagrangian. Although the second term, this is very easy and you can check it easily, that psi bar prime psi prime will remain psi bar psi simply because its psi bar goes to e to the power minus I alpha x psi bar, right. So, the Dirac Lagrangian does not remain invariant under the local or U1 gauge transformation, where psi goes to psi prime equal to e to the power I alpha x psi. And this very feature allows us to construct an interaction between the photon and the electron. Now, the question is, how shall we do that? Before we go into this description, let us remind ourselves of the description of the electromagnetism that we actually had. So, we remember that we actually have a freedom in choosing the photon field or the mu field, because we had, which keeps the Maxwell's equations invariant, right. So, and that freedom was what? That if we make the mu transform to mu prime, which is mu minus del mu chi, or we can say that it goes to mu plus del mu chi, whatever, this is going to keep the Maxwell's equations invariant. So, this is going to keep the whole electromagnetic theory that we have developed, that is invariant, where this chi that we have introduced here is a scalar, and in Lorentz gauge this follows this equation of motion like box of chi has to be equal to 0. Now, this is the key thing to remember while we try to construct a U1 gauge invariant theory. Okay? So, let us try to see how we can do that. So, basically we put up a prescription, and the prescription is as follows, that let us change the partial derivative to a covariant derivative under U1 local or U1 gauge transformation. How? Let us prescribe that this del mu goes to a capital D mu, which is del mu minus I q into a mu. See, in this covariant derivative what we are doing, we are introducing a second term with this field mu, which you can call the photon. Okay? So, this partial derivative is turning into a covariant derivative, and this covariant derivative has the partial derivative as the first term, and the second term is minus I q into mu, where mu is essentially the photon field that we have been talking about. And in terms of this gauge theory, this mu is also called a gauge field. Okay. So, mu, when it enters into the definition of this covariant derivative, is also called the gauge field. Very good. Okay. So, now we define that what is the transformation. The transformation is basically when you take psi to psi prime, which is e to the power I alpha x psi, and then we say that parallelly we are actually having a transformation on mu which goes to mu prime, and that mu prime is nothing but mu plus 1 by q del mu alpha x. So, this del mu alpha x, this alpha is the same parameter that we are introducing here in the transformation of the fermionic fields. So, we are saying that this U1 transformation transforms the fermionic field by e to the power I alpha psi and transforms the photon field or the mu field to mu prime, which is mu plus 1 by q del mu alpha. Now, the legitimacy of this transformation is basically to say that I know my electromagnetic or the Maxwell's equations remains invariant under the transformation of mu going to mu prime, which is mu plus del mu chi. So, this is essentially equivalent of saying that this is nothing but mu plus del mu chi, where we essentially have chosen a specific form of chi, which is like 1 by q alpha x, you can say, right. So, this is what you have for the x, and so therefore, we say that if this is the transformation that we impose on psi and the gauge field, then basically this keeps the Dirac Lagrangian psi bar I gamma mu d mu psi minus m psi bar psi invariant. Let me repeat this statement once more. We first observed that if we make a local or gauge transformation on the fermionic field, the Lagrangian, the Dirac Lagrangian, which is usually defined like psi bar I gamma mu del mu psi minus m psi bar psi, does not remain invariant. So, then how to construct a gauge invariant Lagrangian? We say that first of all, you replace the partial derivative with a covariant derivative, and the covariant derivative has to be defined like d mu equal to del mu minus I q a mu, where we are introducing now this a mu fields, which are called the gauge fields or the photon fields, which is getting introduced to this picture. Now, parallelly, we have to say that this whole Lagrangian is going to transform under U1 gauge transformation, like psi going to e to the power I alpha x psi, and mu is transforming to mu prime, which is mu plus 1 by q del mu of alpha x. Okay. This is going to keep the Lagrangian psi I gamma mu d mu psi minus m psi bar psi invariant. Let us check. So, the claim is that when we transform psi to psi prime and mu to mu prime, the first term, which was the trouble, right, which was the troubling term that we actually had, that is going to remain invariant. Okay. So, that basically means psi bar I gamma mu d mu psi prime remains psi bar I gamma mu d mu psi. So, let us first check that. In order to do that, let us first do this exercise of what happens to d mu psi prime. Now, d mu psi prime, if you understand, is d mu is defined as del mu minus I q a mu, right. So, d mu psi prime will be del mu minus I q a mu prime into psi prime, which is e to the power I alpha x psi, correct. So, this is the d mu prime, so to say, and this is psi prime. Now, let us also remind ourselves that mu prime goes to mu plus 1 by q del mu alpha x. Okay. So, I have del mu minus I q mu plus 1 by q del mu alpha x e to the power I alpha x psi. Now, let us do simple multiplication, which is del mu minus I q mu minus the second term is going to give you the q gets cancelled, and I am going to have minus I del mu alpha x into e to the power I alpha x psi. So, let us take the derivative first. You remember that when this derivative acts, you have essentially two possibilities. First, this derivative will act on this exponential term. So, this exponential term के ऊपर काम करने से क्या होगा? This is going to give you I e to the power I alpha x psi del mu alpha x into psi, right. So, this is what you have for the first term. The second term is simply e to the power I alpha x, and this is going to be simply e to the power I alpha x, and this is del mu psi. And the second term is minus I, the second term is minus I q a mu into e to the power I alpha x psi minus I del mu alpha x into e to the power I alpha x psi. Now, can you see something happening here, and which is very, very interesting for you to observe and note? Look into this last term. this is minus I del mu alpha x e to the power I alpha x psi, and the first term is exactly the same, but the charge is different, so or the sign is different, and so this is going to get cancelled neatly. And what it leaves us? It basically leaves us with a term which looks very nice, that if you take this e to the power I alpha x common, then this is del mu minus I q mu psi. Now, what is this quantity? Del mu minus I q mu is nothing but the defined covariant derivative. So, we are going to get a term like d mu psi prime is e to the power I alpha x d mu psi. So, if we have that d mu psi prime is this, then what happens to psi bar I gamma mu d mu psi prime? So, psi bar prime is psi bar into e to the power minus I alpha x, I gamma mu को रहने देते हैं, and d mu psi prime is essentially e to the power I alpha x into d mu psi. तो इससे क्या होता है कि this alpha x e to the power I alpha x gets cancelled, and we neatly retain the form of the kinetic term, that this is psi bar I gamma mu d mu psi. So, this is what we claimed. This is exactly what we claimed, that when we change this definition of partial derivative to a covariant derivative involving the gauge field and use the freedom of the gauge field transformation together with the transformation of the fermionic field, we basically retain the Lagrangian to be invariant. So, this indeed remains invariant under U1 gauge transformation. So, basically we are saying that the LD, which is psi bar I gamma mu d mu psi minus m psi bar psi, remains invariant under U1 gauge transformation, where del mu has to be replaced by this covariant derivative, which is like d mu minus I q mu psi. Now, the point is, if you inflate this term, what happens? The first term is the usual kinetic term. What happens to the second term? You see that the second term essentially brings forth to an interesting point. This I square becomes minus 1 and this minus becomes plus. So, basically this term gives you q psi bar gamma mu psi into mu, and this is amazingly a very interesting term that you actually see. So, this is the much sought after interaction term of electron and the photon. So, this covariant derivative term that we have introduced in the Lagrangian, that is basically giving you a term like psi bar gamma mu psi into mu. Now, you can remind yourself that this is the term which is actually of the form of j mu a mu, and this is the minimal electromagnetic interaction term that we actually introduced in order to get that Maxwell's equations with the source terms, with the j mu. So, that source is nothing but this interaction, the j mu, which is psi bar gamma mu psi, right. So, this is giving you an interaction of the electron and the photon. Here I also mentioned that there is nothing very pious about the way that we have written this d mu, but we can, for example, define the d mu to be del mu plus I q a mu, and parallelly we can say that okay, what you have to do, that a mu goes to a mu prime, which is a mu minus 1 by q del mu alpha x. So, this is also going to keep the sanctity of this invariance of the Dirac Lagrangian written in terms of the covariant derivative. Okay. So, therefore, we can bring forth the interaction naturally by just doing this symmetry argument, saying that instead of adhering to a global U1 symmetry, if I adhere to a local U1 symmetry or gauge symmetry, then basically this allows me to naturally embed the interaction between the electrons and the photon. And we are going to talk a little bit about the Feynman graphs, or not a little bit, actually we are going to discuss them to quite some extent, but basically it gives you a picture which I have drawn here like this, that it is basically a current which you actually have involving the fermions, which I describes by J mu psi bar gamma mu psi. I am going to discuss all these possibilities, like what it interprets and so on, with a photon field which I have been drawing by this wavy line, and that is going to bring this interaction between the electrons and the photons together. And the question that you can ask is that what does this Q basically indicates? What does this Q stand for, which is sitting here as a proportionality to this electron photon interaction? Now, from your experience of classical physics, you can say that this is nothing but the electric charge essentially carried by the particles, or rather the electromagnetic charge so called of psi. So therefore, for electrons I can say that this Q is nothing but minus E, and so on and so forth. But here that is very interesting. The whole prescription that we talked about is absolutely fascinating, but there is something still missing in the Lagrangian that we have written here, that it is not only this part, but there is something which we have to still include. What is that part? That we should not remember, we should not rather forget, we had a part of the free electromagnetic theory में उसका जो kinetic term है वो भी तो लिखना पड़ेगा, which is like -1/4 f mu nu f mu nu. Now, where f mu nu is del mu nu minus del nu mu. So, the QED Lagrangian, if you want to write the full Lagrangian, will essentially have all the terms together. And all the terms means that first of all you will have psi bar I gamma mu d mu psi, then the mass term minus m psi bar psi, and then you have the kinetic term of the photons, which is -1/4 f mu nu f mu nu, right. So, you remember that in the last lecture we actually had this quantum description of the photons by imposing the canonical quantization prescription. So, once you inflate these terms, what you essentially get is that you have the usual kinetic term like psi bar I gamma mu del mu psi minus m psi bar psi, and importantly we have the interaction between the electron and the photon in the form of Q psi bar gamma mu psi with mu minus 1/4 f mu nu f mu nu, which is like saying that you have a term like plus q j mu mu minus 1/4 f mu nu f mu nu. So, here I would like to therefore remind you that a U1 gauge invariance essentially allows you to bring a quantum electromagnetic theory. So, you remember that we quantized the individual cases, like for the electrons we did this canonical quantization to bring out how the Dirac field can describe the case of electrons. You remember how we actually talked about the quantization of the electromagnetic fields to bring out the photons out of the electromagnetic theory. So, similarly in the full framework that after the gauge invariance imposed onto this Dirac Lagrangian which we just talked about, we can quantize the full theory and have a description of electrons and photons, but now not individually, but with an interaction of the electrons and photons. So, this is no more a free theory, this is the theory that we were actually looking into, that you have the quantum descriptions of the electrons, you have the quantum descriptions of the photons, but they are also at the same time talking to each other via this kind of a Feynman graph. We are going to talk about a little more on the interactions and the Feynman rules of QED in the next lecture, but I think we are going to finish today. So, stay tuned for more interesting discussions on this quantized electrons and photons and how do they talk to each other, and so that we can compute things which we actually really see in the experiments. All right. With this, let us finish today, and I am going to see you in the next lecture. Thank you.